Hello, my name is Himankitav, and today I'll be presenting our work on policy gradient training of fair and unbiased ranking functions, conducted alongside Zhangchao Du and Thorsten Joachims at Cornell University. A ranking is an ordered list of items that are relevant to some query or topic. We have transitioned from using ranking for books and libraries to now ranking products, opinions, job applicants, and even friends and potential romantic partners. Almost all machine learning algorithms today focus on optimizing utility for the user. But with the growing domain of applications, ranking systems have a responsibility not only to their user, but also to the items that are being ranked, since these platforms transfer economic opportunity from one stakeholder to the other. And here's a quick motivating example driving this point home. Consider an online movie streaming service which presents a ranked list of movies for any incoming query. And consider two studios. Studio G1 produces 30 movies that all have relevance 0.7, which means that there's a 70% probability that the user will want to watch each movie. And Studio G2, which produces also 30 movies, but they all have a slightly lower relevance of 0.69. Still comparable, but slightly lower. Ranking purely based on relevance to the user would put movies from G1 at spots 1 to 30 and movies from G2 at spots 31 to 60. Leading to a much higher exposure and revenue for movies from G1 than from G2. Exposure translates to opportunity, and unfair exposure means unfair opportunity. Exposure is largely determined by the position in the ranking. This can be considered unfair, since movies of almost equal merit, that is relevance, receive disproportionately worse outcomes, that is streaming revenue. There is a need to study the impact of rankings on the items being ranked by incorporating some notion of fairness. And to increase the well-being of an online platform, we need to strike a balance between the two aspects. A first thought for addressing the shortcoming may be to enforce various forms of demographic parity between the groups of items in the ranking. However, allocating exposure without considering merit has other undesirable effects. Consider this. Assume there's like a third incompetent movie studio that also has 30 movies with a low relevance of 0.1. Clearly, these movies do not deserve as much exposure as those from Group 1 and Group 2. To combat this, we follow an approach that explicitly links exposure to merit of a group. Specifically, merit-based exposure allocation can ensure that groups of similar merit have similar outcomes. Enforcing merit-based exposure is a factor endogenous to the ranking system, meaning that it is fully under control of the system designer. However, it relies on accurate estimates of merit, which can be affected by exogenous factors. Consider this, for example, a situation where movies from Group 1 have been ranked consistently higher than those from Group 2 in the past. If we now naively count the number of clicks as an estimate of merit, this estimate will be biased by how humans browse their lists. In particular, these movies from Group 2 are likely to get substantially fewer clicks than those from Group 1. Not because they're substantially worse, but because they're less likely to be discovered by the users. In this way, even an endogenously fair system can become unfair, as its past actions create biased estimates that amplify these inequalities that can lead to more general undesirable effects. In this paper, we simultaneously address both endogenous and exogenous causes of unfairness and present the first learning to rank algorithm called FULTR, which stands for Fair Unbiased Learning to Rank, for unbiased learning from locked implicit feedback that can enforce merit-based exposure allocation constraints. Here's a quick outline of our framework that we'll talk about. First, we'll begin by visiting our objective. Then we will touch on our unbiased utility and fairness, utility estimator and fairness constraints. Then we'll talk about relationship with other disparity measures. Next, we'll discuss the relevance of click noise, followed by Takeuchi ranking model. And then finally, we'll talk about our policy gradient training algorithm. We define our objective by combining the fairness constraint with conventional utility optimization. Like in conventional LTR algorithms, our objective is to learn a policy from the policy space with high expected utility. However, focusing on utility optimization for users does not by itself guarantee fairness to items like we have seen before, which is why we include an additional constraint that addresses unfairness. A perfect ranking policy has zero disparity. We want to restrict the square of our disparity term to be at most some threshold delta to get our disparity as close to zero as possible. Note that directly optimizing this objective is not possible, since neither the query distribution nor the relevances are known, which is why we take an ERM approach where the terms, the utility term and the disparity term, are replaced by estimators based on a partial information training set. Next, we'll talk briefly about our unbiased utility estimator. One quick note here is that we consider the space of stochastic ranking policies because they have the advantage of providing more fine-grained control of exposure and enabling gradient-based optimization. And in the case of a partial information setting, since we do not know the relevances, we can only observe clicks. We introduce a new binary random variable that indicates whether the item is examined by the user. Based on this, we can model the propensity of observing an item given that the ranking was presented when the item feedback was logged. And with the knowledge of this propensity, we can then use IPS or inverse propensity score weighting to arrive at the following estimator of the utility. Next, we'll talk about unbiased fairness constraints. As a first step, we define the merit of an item as its relevance. The exposure of an item in a ranking is the probability of the user examining the item in the ranking. The exposure term here is the expected exposure over all possible rankings, and the exposure of a group is simply the aggregate of exposure of the group members. The disparity term here formalizes the principle that proportionality between merit and exposure should hold true for a fair ranking. We need to estimate the disparity term with respect to the unknown query distribution and unknown merits, and we can get an unbiased term of the merit using the IPS estimator. Note that the unbiased disparity term is also unbiased since the merit term is unbiased and the exposure terms are non-random constants. Next, we'll briefly contrast our disparity measure with some existing disparity measures. Here's a disparity measure, disparity treatment constraint from Ashadeep et al. Evaluating this constraint requires the knowledge of full relevances, which is often unfeasible to decipher from real-world implicit feedback. And directly replacing the relevance term with clicks when evaluating merit leads to biased estimation due to selection bias, like we noticed earlier. To combat this, naively plugging in the IPS estimator into the corresponding disparity measure would not eliminate the bias effectively. For an unbiased merit estimate from clicks, we need to know the joint distribution of observation for all items in the group, which is difficult to model. Instead, our disparity estimator has an unbiased estimator to overcome this selection bias. Another disparity measure replaces the query-specific exposure and merit with an amortized notion over the query distribution. This measure expresses that for all queries, the amortized exposure of each group should be proportional to its amortized merit. However, this requires the true knowledge of relevance labels and does not involve learning. Extending this approach to learn relevance can suffer from a two-step approach that relies on post-processing and unfair estimation to make it fair, since fairness constraints are not taken into account during the learning process. Next, we will discuss the incorporation of click noise. Up until now, we assumed that positive feedback reveals the relevance labels in the noise-free way. That is, a user clicks only and only if an item is relevant and they're able to observe it. However, in practice, a user might make mistakes when examining the relevance of items, and we now define the following noise model. If epsilon positive is less than 1, users might ignore relevant items even after examination. In the opposite case, where epsilon negative is greater than 0, users might give false positive feedback to irrelevant items after examination. The IPS estimator of utility is order preserving for two policies. Therefore, given enough data, the click noise does not affect the ability to find ranking policy with optimal utility. In contrast, the disparity estimator is not order preserving when false positive noise or epsilon negative is greater than 0. However, if we know the level of negative noise, we can correct the IPS estimator for group disparity as stated on the slide. And to estimate this epsilon negative for false positive noise, we can use existing simple intervention techniques. So far, we have defined a general framework for learning ranking policies from biased and noisy feedback under amortized fairness constraints. We will still need to define an efficient algorithm to search the policy space for solution to the training problem. And to do so, we first define a stochastic ranking policy space based on the Packet-Luge ranking model, and then present a policy gradient approach afterwards. The probability of ranking is defined as a product of its softmax distributions. To sample from rankings, we can sample items from the distribution softmax without replacement, and then rank items in the order in which they were drawn. We use stochastic gradient descent to iteratively update the parameters of the ranking policy. However, it is intractable to compute the expectation of the utility estimate term and the disparity estimate term over the exponential space of rankings. And to combat this, we use the log derivative trick of the reinforced algorithm to compute the gradient of these terms. To collect empirical evidence, we conduct various experiments onto real-world datasets. We use the Microsoft Learning to Rank dataset, which is a very large-scale popular LTR dataset, and the German credit dataset, which is a popular credit scoring dataset often used to study algorithmic fairness. To generate click data, we train a ranking SVM with 1% of the full information training data as our logging policy. This policy is then used to generate rankings from which the click data is logged. The performance of these methods is reported on a full information test set for which all relevance labels are known. Ranking utility and fairness are measured with average TCG and the squared disparity term. In our first set of experiments, we try to answer the question whether FULTR can learn accurate ranking policies from biased feedback. We ignore fairness and focus entirely on utility, just like conventional LTR. For realism, we also inject some noise of a negative epsilon of 0.1. We compare our method with existing baselines, lambda rank, propensity SVM rank, and PG rank, and we establish that FULTR can indeed be competitive with these baselines without fairness constraints when learning from partial feedback. And this implies that FULTR is a promising contender for use in practical applications. Next, we investigate FULTR's ability to enforce merit-based fairness of exposure. Here, we compare with a few methods as baselines. One of them is a group-blind method, where we have FULTR without any fairness constraints, and we assert fairness through unawareness. We have fair PG rank IPS, which is the fair version of PG rank with naive IPS, and then another method for equity of attention. Here we notice that the group-blind training does not lead to merit-based fairness of exposure, and FULTR is able to effectively trade off the utility and fairness on both datasets. As our lambda increases, the disparity decreases with an associated drop in our DCG, and increasing our lambda further drives the disparity to 0. The neural network version, FULTR MLP, achieves a better utility fairness trade-off than the linear version. The German credit dataset was not large enough to train a reliable MLP model. Next, we will talk about convergence. We explore how ranking utility and fairness of FULTR converge as the amount of click data increases. The policy learned by FULTR in a full information setting serves as the skyline that has the full knowledge of all relevance labels in the training set. Here we establish that increasing the amount of click data, FULTR approaches the skyline performance of the policy learned, which means it is able to converge to the full information setting. Next, we had spoken briefly about noise. We investigate the effectiveness of a noise-corrected disparity estimator that we proposed to handle click noise. And we show that the noise-corrected IPS estimator of the disparity can indeed reduce disparity effectively and achieve zero disparity. While the pure IPS estimator cannot do that, even with an increased 3x data. Finally, we talk about how our framework deals with multiple groups. We compare our utility fairness trade-off for a varying number of groups. We observe that given a fixed number of training clicks, the disparity of FULTR increases as the number of groups increase. This is because the training data is fixed and the number of groups are increasing. We also demonstrate that FULTR can deal with multiple groups, but an increase in the number of groups also requires an increase in training data. To sum up, we presented a framework for learning accurate and fair ranking policies from biased feedback. We introduced fairness of exposure constraints that can allocate amortized exposure to groups of items based on their amortized relevance. Next, we proposed counterfactual estimators for corresponding utility and disparity measures that remove the effective position bias and click noise. For training, we derived a policy gradient algorithm that optimizes directly both utility and fairness. And finally, we presented extensive empirical evidence that FULTR can learn effective ranking policies under fairness constraints despite biased and noisy feedback. Thank you.